Well, you know, as we get up higher up in the atmosphere, he's up around 30, 40,000 feet, we find that due to that lower atmospheric pressure up there, as Kevin mentioned, we have less oxygen, but also we have less pressure that can affect other things in our body besides just breathing. And we're going to do a little experiment to look at that. But first, let's get back down to Earth here, and let's talk about what it's like here on Earth. Well, you know, we talk about atmospheric pressure and pressure on us here on Earth. How much pressure, Kevin, do you think there is here on Earth?
Well, it doesn't feel like much.
It doesn't look like much at all, does it? No. But, you know, if I take this little square inch here that we have, and I ask you to take this weight,
Wow, that's heavy.
it is. And if on every square inch we have here on Earth, there's that much weight pushing down on us, 15 pounds per square inch. So on our liquid we have in the jar here, our simulated little cockpit, we have 15 pounds per square inch pushing down on us here.
For every inch? Wow.
So we want to take a little experiment now. Let's take away that 15 pounds per square inch, and we're going to start removing pressure from us by taking out air molecules from this jar to simulate climbing up an altitude like we're leaving the Earth here. So as our plane takes off and we start flying up, we go higher and higher. We get up around 10,000 feet, going up to 20,000 feet. As you mentioned, less oxygen is available, and then we start going above 20,000 feet to 30,000 feet. Wiley Post would have needed some extra oxygen to breathe so he wouldn't lose consciousness. And then as he gets up to 30 to 40,000 feet, he'd want some pressure in that suit in order to push that oxygen and make sure that he breathes well enough. And then around 50 to 60,000 feet, what happens?
Looks like it's boiling.
Yeah, the liquid in his body, if you're up around 63,000 feet, your body temperature gives that liquid enough energy to actually boil. And, you know, that's all because of that reduced pressure. Well, let's bring us back down here to Earth, and let's just talk a little bit about what we see here. I'm going to let air pressure back in this container, back in our cabin, so we'll simulate coming back down here to Earth.
Now that liquid was boiling. It's got to be hot now, doesn't it?
I'll tell you, it's not.
I sure don't want to touch it.
Let's let Kevin.
Sure
let's
you do.
let-
Come
I-
on, come
I think
on,
we'll
Kevin.
let Kevin find
Kevin
out.
will do it. Come
All
on.
right.
Yeah.
Oh, it's not hot at all.
Not.
It's room temperature.
Oh, gee, why could that be?
I don't know.
Yep. Well, I'll tell you. What happened here is that instead of heating up the molecules and letting them move faster to boil, we removed that 15 pounds per square inch pressure from the top of that liquid, and now the air molecules inside that liquid, all that stuff just started bubbling up and coming out of solution. So again, pressure suits like Wiley Post created back in 1935 had to solve two problems: provide oxygen to breathe so he wouldn't pass out, and also provide pressure so that your liquid in your body doesn't boil, and also provide pressure to push that oxygen into your lungs so you can stay oxygenated and so you can breathe well at high altitudes. Well, you know, the stuff that Wiley Post did in 1935, we see nowadays in our current space suits that we have now. We have a launch recovery suit here used for taking off in the space shuttle, and we also have a space suit called the Executive Mobility Unit here, our white one, that we use in the space shuttle and also on the International Space Station when they're outside doing work outside in the atmosphere. That's what they're using to stay pressurized.
Now that's pressure suit. You feel it. It's just a normal fabric. How does it work?
Well, the pressure suit works in a manner in which, if you look at this, I can show you pretty simply. There's a rubber bladder, just like you mentioned with Wiley Post. B.F. Goodrich developed a rubber bladder for Wiley Post. There's a rubber bladder here that holds the pressure and maintains that pressure that's fed into here, and also maintains that oxygen flow in the system. And then this garment on the outside actually maintains the shape of the pressure, the shape of your suit, so it doesn't just balloon out as you start to add pressure and you're being held by that rubber bladder. And this same technology we use in the launch and recovery suit worn by our astronauts taking off and landing in the space shuttle is the same type of thing that's incorporated into the spacesuit here that we have when they're working outside the International Space Station or they're going up for a spacewalk. That same technology, the rubber bladder and the protection. The big difference here with the white suit, which we'll talk about in future segments of the show, is that this white suit also is made of Kevlar. And the Kevlar in the white suit is used as a protection device to stop little micrometeorites from penetrating the suit, because you never want to break that rubber bladder seal, because then you would lose your pressure, you lose your oxygen, and the problems we saw here in our experiment would all of a sudden be for real again.
Yikes.
So along with supplying the pressure, that outside spacesuit it's almost like armor for the astronaut.
It is. It provides that protection, both physical protection like armor, as well as that thing to hold the pressure, hold that oxygen in. And also in the suit like the astronaut uses, there's also what's called a liquid cooling garment that actually also controls your temperature. That's the other thing when you're in space you have to control. Just like Wiley Post, when he flew in the Winnie Mae, had to wear very heavy clothes to stay warm, because as you climb up in altitude, besides for the pressure and the oxygen becoming less, your temperature goes down.